In this video, we'll be discussing the chi-squared distribution and specifically how it relates to tests of categorical variables. Now, typically chi-squared is broken into two tests, the test of independence and the goodness of fit test. In this book, they talk about using it to compare more than two proportions, so kind of like an ANOVA for proportion data, which is just fine. What that ends up being, though, is a test of independence. Actually, a test of independence is a little bit more flexible than that, and we'll discuss how this relates. But that is a good jumping off place intuitively to figure out what this test is doing and how we can put the components together. Now, the different thing about the chi-squared tests, all of these, is that think like an ANOVA situation where we have an independent variable that's a categorical factor with multiple levels. In chi-squared, instead of the outcome being continuous, as it was in ANOVA, now the outcome is going to be categorical. So we're looking to compare two or more categorical variables to one another. And in this lecture, we're only going to talk about comparing two categorical variables. Because of this, chi-squared is actually really flexible. It's not particularly statistically powerful, but it is broadly applicable. Maybe the Bonferroni of statistical tests. Why is this? Well, this is because if I have continuous data, let's say I've got GPA that I'm studying, and I'm studying that as a relation to your eventual salary that you'll make in your future career. And I want to look at a relationship there. Well, for an ANOVA, I would require one of the variables to be categorical and one to be continuous. And in this case, they're both continuous, so I could make that happen. I could change GPA into low, medium, and high, and leave your salaries continuous and break that into three groups: low GPA group, medium GPA group, high GPA group, and study your salary in those groups, and that would work. Well, with the chi-squared distribution, you can do the exact same thing. That is, any data that's continuous can be made categorical. Here's the benefit to the chi-squared, though. Let's say I'm looking at your favorite color, red, blue, and yellow, and how that relates to your favorite pizza topping, pepperoni, sausage, or anchovies. How could I study that with a statistical test? Well, I might think, well, a t-test, I've got, or an ANOVA, I've got more than three groups, so red, blue, and yellow, and I want to look at the distribution of the different pizza toppings. But I realized that my pizza topping, that outcome, is not categorical, or is not continuous. It is categorical. So I'm unable to actually analyze that data using an ANOVA because the outcome is categorical instead of continuous. What this highlights is that because chi-squared can handle such a distribution, can handle such a question, chi-squared can handle everything that ANOVA and regression can, but chi-squared can do it and handle all of the categorical things. Now, chi-squared is a pretty basic test, but it is extraordinarily flexible, so it's a really good one to have in your toolbox in case you need to break something down into the groups and look at it that way. Now, this said, chi-squared is not the most descriptive because it requires groups. Now, if your data are categorical anyway, this works fantastic, and this is what the chi-squared was made for. If your data are continuous, though you can make continuous data categorical, that really loses a lot of information. So we really don't like to do that unless we absolutely have to. But as an old professor of mine once said, if you had to take one statistical test onto a random deserted island with you, maybe chi-squared would be that test because it really can handle any kind of data. We can always make continuous data into categorical data and then run the chi-squared. So it can handle anything you can throw at it, even if it's not the most appropriate test for many cases. So let's start with the proportions. So for proportions, one of the things I want you to remember is how we calculated proportions. So we calculated proportions as the number of successes over the total number. And this goes back to your previous stats class. Or just kind of your general way of calculating proportions. So if I flip a coin 100 times and 51 of them are heads, there's a 51% chance of getting a heads, and I'll define heads as a success on that particular case. The definition of success changes. Well, what's interesting is if we have this, we can actually also calculate the number of failures. So if we have number of success, number of failures, and note, by the way, that number of failures and successes, it doesn't have to be a good thing. So sometimes, actually, I've studied in a medical context survival, and we look at and death, and we look at death as a proportion of interest, how many people died. Well, in that case, death would be a quote-unquote success according to this terminology. So success isn't meant to be success as in, yay, you're successful. Success is meant to be more the frequency of interest, and I say number of successes just as a shorthand, but it is the number of times the thing you're interested in happened. And similarly with failure. Failure doesn't mean a bad thing. Failure just means the number of times the thing that you're interested in didn't happen. So if I take the total number minus the number of times what I'm interested in happened, I get the number of times that something I'm not interested in happened. So this is the number of failures. And I can do that for each of the proportions. So what we're going to look at is among these proportions, you can do this for 3 or more. You can also do this for 2 proportions. Can we determine if there's a difference between these? So for instance, we'll look at this example with different homes. So we've got people who are considering repurchasing a colonial home, repurchasing a log cabin, and repurchasing an A-frame. And we want to see how many people liked their home enough that they would say, yeah, I'd buy that again. So we get our data. And this is a common way that you'll see data presented sometimes. Now, sometimes what you'll see is you'll see like a percentage. So let's say 97 over 135 turns out to be, I don't know, 80% or something like that. So we'd see 80% and then the sample size of 135. Now, given a percentage and a total, I can multiply that. 80% times 135 would give me this number back. And then using this number, I could do that previous equation. We talked about total minus this number to calculate the number of no's. So if I have just a percentage and the total number, I can calculate all of the information in this column. And that's important to recognize because we're going to be using the number of yeses and the number of no's in this statistical test. So we need to have it written out in this format. Incidentally, this format is called a crosstabs. So it's got a table that crosses how we present our information. So we've got the 2 variables, the type of home, and then we have whether or not the individuals would repurchase. And we kind of cross, and then the number in the table indicates how many people fall in both of those categories. So in this case, how many people fall within the colonial homeowner and yes, I would repurchase category. So there were 97 people that when I gave them a survey, they checked yes, I'd repurchase, and they checked I have a colonial home. And that's actually what this data would look like if we entered it raw, is we'd have a whole bunch of lines, a whole bunch of rows in a spreadsheet, and then a one column I'd have repurchase, and then I'd see yeses or nos. Then in another column I'd have type of home, and there'd be log, colonial, A-frame, all the way down. And there would be 97 rows that looked identical. That is 97 rows that have a yes in the first column and a colonial in the second column. Now, the equation that we're going to use as part of this calculation is this row total times the column total over the sample size. So this calculates not the error. So we talked about E as error previously. This calculates the expected value of what the count would be in that cell. So what we're going to do is this assumes that each of the rows are equally likely inside each of the columns. Or, said another way, this assumes that all of the probabilities for each of the columns are the same. So we calculate what's the expected count assuming all of the probabilities are the same. So using math theory, what would the expected count be in each of those cells if all the probabilities were the same? And then we're going to see how far is the difference between what we actually observed and what we expected in this. So running this formula, I take the total number in likely to purchase times the total number of colonial homes, so 260 times 135, and then divide by the total sample size, 360, and that's how I get the expected number of colonial homeowners who answered yes, 97.5. And I would do that for each of these column row combinations. So for each cell, I would go to that cell, I'd look at the row total, I'd look at the column total, I'd multiply them, and then divide by that total number. From here, with the expected values, now I can calculate my chi-squared statistic. So pretty much what chi-squared does is it takes my data that I observed, so that first table, it subtracts that data that I calculated as expected, assuming that all the probabilities were the same mathematically, and it subtracts the two. So this is asking how far off are my values from what I expect to see. Then it squares each of those differences to make them all positive, and to make them all positive is what we say. There's a question, why don't you just use the absolute value, which is a really good question. Actually, that is another statistic you can calculate, but it has a different distribution. Anyway, so we square them to make them all positive. And then we divide them all by the expected value to say how far off from the expected value is this difference. Last step, so we calculate that for each one of the cells, then we add it up for all the cells in all the rows and all the columns. And that's what our chi-squared is. The observed minus expected squared divided by the expected. And actually, how I learned it was O minus E. You can see why I don't write with my computer pen very much. But the sum of the observed minus expected squared divided by the expected. So that's what's going on here. Observed, in our textbook they call it the frequency, or F. E expected, observed minus expected squared over the expected. So in this particular case, we have each of these. Now, instead of writing it as tables, they've gone ahead and written it out as columns with the observed frequencies here, but you'll notice that if you went on the table and found likely to repurchase yes, the type of home is a colonial, then you'd find a 97 entry in that table. They're just writing it out the long way, or the longer way. There's three forms of data. We'll talk about this in the R section. Then we have the expected, and then we just follow through the steps. Observed minus expected gives me the difference. Then I square that difference, and then I divide by this expected column. So this squared value, 0.25, divided by 97.5 gives me 0.0026. And then I add all of those up to get my chi-squared statistic. So I find the critical value is, I don't like this, the significance level k minus 1 degrees of freedom. Actually, this is the row number minus 1 times the column numbers minus 1. Now, because in a test of proportions, the rows minus 1 is always going to be 1, they just ignore this in your book, but this is the equation we're going to be using for the rest of this lecture. So this is a good way to practice it. I have 2 rows minus 1, that gives me 1. I have 3 columns minus 1, that gives me 2. So in this case, I'm going to have 2 degrees of freedom, and I would not use this k minus 1 when I'm doing my chi-squared. I just set it up like this. So looking at this, it's our traditional values that we use. This isn't a 1 or 2-tailed test, nothing like that. We're just doing the test, so alpha equals 0.05 or 0.10, but you don't have to make any adjustments like divided by 2 here. You can look on a table or look in R. So in this case, my chi-squared value is between these two values for P. So we'd reject the null hypothesis. If I look this p-value up for this chi-squared in R, or if I ran it in a statistical software, I get p is 0.0131, and at alpha equals 0.05, the p-value is less than alpha, which means we reject the null hypothesis. And if you're still struggling with this, that's okay. Just write it down somewhere big at the top of your notes so you can go back, because we use a lot of p-value comparisons to alpha. If p is less than alpha, we reject. That means something interesting happened. If p is greater than alpha, we fail to reject, and that means we can't make conclusions against that null hypothesis, or everything's the same. So in this particular case, because we have a statistically significant result, we can conclude that the three populations are not the same. And we'll end here for today. So we'll pick up in the next video on multiple comparisons procedure, so how we can compare these. In R, we'll do this a little bit differently, but we'll talk through the theory and then move on to our first more traditional chi-squared test.